This galactic feeding is supposed to happen as follows. The small black holes bind stars in the outer regions of the Milky Way, which lead them on their orbit to the immediate vicinity of Sagittarius A star. Once there, some stars are finally detached and consumed by the elemental forces of the supermassive object. The cosmos is known above all for two characteristics: its exuberant diversity and the elemental forces at work within it. When a massive star has reached the last stage of its natural span of existence, it seals its own end with an explosive farewell, a so-called supernova. The findings that experts obtain in the course of studying these stellar deaths regularly bring home to us the fascinating uniqueness of such spectacles. In today's video, we'll show you how researchers recently succeeded in identifying a new nova record holder and the sheer incredible emissions that were released during the process. When stars die. Once a massive star enters the final chapter of its cosmic life, it's time for a brutal, radiant farewell. The process of supernova refers to the short-lived, intense illumination of a star that comes from a gigantic explosion. How extreme these stellar deaths can be becomes clear to us if we keep in mind that the luminosity of the celestial body can increase billions of times in the course of a supernova. Sometimes the star briefly shines even as brightly as a full-grown galaxy. Within a few seconds, about 1 pho of observable energy is released. To understand how this value fits into the overall galactic context, it's worth taking a look at our Sun. If our host star would have its current luminosity during its whole lifetime, it would release about 1.2 pho of energy. As a reminder, it's estimated that the Sun's own fuel is sufficient for a total of 10 to 13 billion years. Basically, there are two basic mechanisms that can cause stars to go supernova. On the one hand, there are those stars whose initial mass is more than 8 solar masses. If the nuclear fuel of the celestial body is completely used up, its life ends in the course of a so-called Type II explosion. After the hydrogen in the stellar core has fused into helium, the internal pressure of the star also drops dramatically. As a result, the celestial body collapses under the influence of its own gravity. The resulting increase in temperature and density in turn sets another fusion stage in motion, the 3-alpha process. In this process, 3 helium nuclei are converted into carbon by nuclear fusion reactions inside stars, emitting gamma radiation. This process repeats a few times, with carbon burning to form neon. Finally, after a series of further fusion processes, the time comes when the stellar burning processes come to a complete halt. As a result, the hydrostatic equilibrium of the star is severely affected. The oppositely acting gravitational pressure literally presses the celestial body into itself. As a result, the outer layers also fall towards the center, where they finally come into contact with the hottest part of the star, the iron-nickel core. However, the incoming shock wave is thrown back by this massive, dense stellar heart, setting off the classic stellar collapse supernova as the shock wave now bounces outward. What remains of the progenitor star after this glistening explosion is decided by the remaining mass, which collapses. Usually, stellar death ends in the formation of a neutron star, which typically weighs between 1.2 and 2.0 solar masses. Due to their extreme compactness, these stellar remnants have radii of only 6 to 7 miles. Moreover, these objects are the densest known formations without an event horizon. Besides their strong magnetic fields, neutron stars are known for one special property: their insane intrinsic rotation speed. The current record holder in this category achieves an incredible 716 revolutions per second. This corresponds to almost a quarter of the speed of light. However, it's also possible that the death of the star will result in the birth of a stellar black hole. These equally fascinating and frightening formations are created when the star's core collapses into an incomparably compact body due to its gravitational pressure. The gravity generated by this compactness is so strong that black holes become galactic omnivores. Nothing that has passed the event horizon of a black hole can cross it again from the inside out. When exactly the progenitor star meets its prescribed fate is defined by its initial mass. The heavier the star, the shorter its cosmic life expectancy. Type 1a supernovae. As mentioned earlier, in addition to this well-known basic mechanism, another exists that can transform a star into a supernova. while the Type 2 explosion is still due to the drying up of stellar fuel and the associated consequences. A Type 1a supernova involves two celestial bodies at once. This double star system consists of a white dwarf and its companion. As a reminder, white dwarfs are small, compact old stars with very low luminosity. Over the years, the white dwarf accretes more and more gas from the expanding envelope of its companion. As a result of this transfer of material, several nova outbursts can be set in motion, a term that should not be confused with the term supernova. A nova describes a burst of brightness in a binary that originates from an explosive ignition of hydrogen burning on the surface of a white dwarf. In the course of these outbursts, the hydrogen of the ingested gas thus fuses until the white dwarf has enriched its core with enormous amounts of contaminated carbon. Further combustion and accretion processes cause the stellar core, which now resembles an oversized diamond, to become steadily more unstable. Once the limiting mass is reached, the entire carbon supply is burned to nickel and iron within fractions of a second, which means that it detonates as a Type 1a supernova. Unlike a core collapse supernova, however, no compact object such as a neutron star or stellar black hole remains. The matter of the dying white dwarf is completely catapulted into the gigantic expanses of space. Also, the companion star is not unaffected by this primordial event. It transforms into a so-called runaway star due to the high orbital velocity with which it once orbited the white dwarf before. It literally flies away. Violent nova eruption. Now that we have taken a look at the two best-known basic types of supernovae, it's time to take a look at an exciting discovery that researchers made just a short time ago. In detail, the researchers were dealing with the precursor of a Type 1a supernova. The system that became the focus of scientific interest is called RS Ophiuchi, as the researchers from the Max Planck Institute in Munich discovered during their investigation. The nova outbursts were accompanied by an unusually intense emission of gamma rays. About 5,000 light-years from our blue home planet, a white dwarf in the eponymous constellation Ophiuchus incessantly accretes material from its companion, a red giant star. As briefly described earlier, the absorption of hydrogen gas on the surface of the white dwarf sometimes leads to overheating that sets off violent thermonuclear explosions. These violent events usually follow a fixed cycle. In the case of RS Ophiuchi, about 15 years elapse between nova eruptions. Finally, the most recent nova observed by experts was accompanied by an unexpectedly high gamma ray burst. In detail, the emission, which was registered and analyzed with the help of the two magic telescopes on the Canary Islands, reached an incredible value of 250 giga-electron-volts. This is one of the most intense gamma ray bursts ever observed by astronomers. The explosion produced shock waves that accelerated particles to near the speed of light. Based on their collected data, the scientists concluded that the gamma rays originate in energetic protons, the nuclei of hydrogen atoms. In other words, nova eruptions are also sources of cosmic rays. This means a high-energy particle radiation, which is mainly composed of protons, but also of electrons and completely ionized atoms. The corresponding particles move through the gigantic expanses of the cosmos at almost the speed of light. Compared to the enormous shock fronts generated by supernovae, however, the forces released by nova outbursts are significantly less intense. One day, RS Ophiuchi will also be torn apart as part of a Type 1a supernova. However, a look at the experts' next discovery shows that not all objects want to follow the supposedly fixed rules of the cosmos. Stellar death throes. When a massive star goes supernova, it shines brighter than full-grown galaxies for a few days, before rapidly losing luminosity afterwards, a supposedly fixed scheme, which went completely ad absurdum. In the case of the object IPFT-14HLS, astronomers like Stan Woosley, who dedicated themselves to the investigation of the structure, called this simply bizarre. The background? It seems as if the star in question simply does not want to die. Originally discovered in September 2014, the stellar explosion was initially thought to be a perfectly ordinary supernova. However, when an attentive intern sifted through the collected data, again 5 months later, he came across a puzzling detail. The supernova first became fainter, as expected, only then to shine brighter again afterwards. Even more puzzling is the fact that this was not a one-time phenomenon, but a reoccurring one. Over an observation period of 2 years, this interplay of dimming and intensification was registered 5 times. The analysis of the light spectrum paints a clear picture and perfectly matches the basic characteristics of supernovae, ruling out any other event. Never before have experts been confronted with a supernova lasting years. Normally, dying stars go out completely after about 3 months. But that's not all. A review of archival images showed that another stellar explosion had occurred at exactly the same location in 1954, but had been overlooked at the time. The question of what is behind this supernova hiccup is still the subject of research. Now we want your opinion. What do you think about the stellar explosion spectacles that regularly occur in the cosmos? Drop us your thoughts, suggestions, and feedback on today's video in the comments below. Still in the mood for more exciting contributions on the topic of outer space? Then take a look at the other videos on our channel, which we have linked for you here in the credits. Thanks for your interest, take care, and we'll see you next time.